Dr. Casey Kerrigan is a Harvard Medical School graduate with a master's degree in kinesiology, the study of body movement. Dr. Kerrigan is known internationally for her peer-reviewed published research on gait, the study of walking and running, and the effects of footwear on the joints in the body. Casey published her first research paper in 1998, demonstrating a link between high heels and knee arthritis. She subsequently discovered that even a small heel elevation, as well as a lot of other features in traditional shoes, similarly increased impact on the joints. Casey's research, along with her years of clinical experience treating the wide variety of problems linked to poor footwear, led her to develop and launch OESH shoes. From her Charlottesville, Virginia facility, Casey and her team designs and manufactures OESH footwear with the help of Visual Mill from MecSoft Corporation. We recently sat down with Dr. Kerrigan to discuss her remarkable contributions to the footwear industry and her use of our Visual Mill software. In 2009, Casey was the first woman tenured professor and chair of the Department of Physical Medicine and Rehabilitation at the University of Virginia. Casey was also professor of mechanical and aerospace engineering when she left UVA to concentrate full-time on footwear development. When it came time to prototype her footwear sole designs, Casey taught herself CAD/CAM. She then purchased a Supra 3-axis vertical mill from CNC Masters, who highly recommended that she take a look at Visual Mill from MecSoft Corporation to generate the 3-axis cam toolpath she would need to machine the sole design molds her footwear required. Here we see the OESH Levita shoe design and mold plate. Here's a sample of what Casey had to say about Visual Mill.
I've trained two different people, and neither one of them have had any trouble learning it. Yeah, we've been happy, and that's, I guess, the other thing. Yeah, what we've been really excited and why we really wanted to stick with MecSoft is really because of that your 4th-axis continuous milling.
Thanks, Dr. Kerrigan. Visual Mill helps OESH design their 3D printers. Dr. Kerrigan has also developed her own production 3D printers that OESH uses to produce the soles for their line of 3D printed sandals. With a grant from the National Science Foundation, Casey was able to refine the development of her thermoplastic extruder that her 3D printers required. Here we see Dr. Kerrigan inspecting the bulk thermoplastic pellets used by the OESH 3D printers. On the right, we see the OESH Athena 3D printed sandal in poppy white. Casey also taught her apprentice, Maggie Rogers, how to use Visual Mill. Maggie is a recent UVA graduate, designer, and fabrication specialist with OESH. Maggie assists in the development of the company's 3D printer extruder designs. All of the G-code required to machine the design components were generated in Visual Mill using 2, 3, and 4-axis toolpath strategies. Here is what Maggie Rogers had to say about Visual Mill. The thermoplastic heater block design shown here is a great example of how Visual Mill's 2.5-axis toolpath strategies can be used to quickly and effectively rough and finish a complete 3-dimensional component. Maggie is using Visual Mill's roughing, profiling, hole pocketing, drilling, chamfering, and thread milling toolpath strategies on this component design. This is just one of the components that OESH has developed for the production 3D printers the company uses to manufacture the 3D printed line of sandal footwear. Maggie generated the G-code required for their CNC Masters Supra 3-axis vertical mill using the CNC Masters Inch post processor, one of over 300 posts included with Visual Mill. Here we see Visual CAD/CAM with the Visual Mill CAM plugin loaded. The thermoplastic heater block 3D model is loaded, and one of the 2.5-axis profiling toolpaths is shown, with the cutting tool displayed. On the left, we see the Visual Mill machining browser, showing the machining job and the toolpath editor. On the right, we see the cut material simulation for the 2.5-axis chamfering operation and the actual component machined from 6061 aluminum. The thermoplastic heater block incorporates an interesting mix of 2.5-axis toolpath strategies. In the machining job shown here on the left, we see that it starts with an initial roughing toolpath and then continues with the profiling, hole pocketing, drilling, chamfering, and thread milling to complete the machining job in one setup. In the first two images, we see the 3D part model displayed along with the box stock model. Cutting begins with the 2.5-axis roughing strategy using a 3/8" diameter end mill. The pass uses offset cut patterns, mixed cut direction, a 50,000 step over, and a 100,000 step down, with a stock allowance of 10 thousandths. A straight vertical approach is used, coupled with linear XY extensions. Next up are 3 profiling strategies to make finished perimeter cuts using the same 3/8" diameter end mill. All have a mixed cut direction, radial entry and exit motions, a step down of 50 thousandths of an inch, and a finished stock allowance of 0. To prep for the minor diameter of the 5/8 internal thread at the top of the heater block, a hole pocketing strategy is used. Again, with the 3/8" diameter end mill, this path is a helical motion with a cleanup pass at each cut level of 30 thousandths of an inch for a total depth of 1.2441. The cut parameters are illustrated in the dialog icon shown here on the right. The path also includes a helical entry and a vertical retract. Next up are the 3 center drilling operations using a 0.156 diameter drill, the first of which is shown here. Each has a center drill depth of 100 thousandths of an inch. Following this are 3 deep drilling operations, each using different drill tool diameters. The first operation is shown here. Each has a step increment of 50 thousandths of an inch, similar to peck drilling, and an approach distance of 0.1. In further preparation for the 5/8 internal thread, a chamfer operation is added to the top inner perimeter of the larger center hole, using a 30-degree V-mill at a depth of 40 thousandths of an inch. To complete the setup, a 2.5-axis thread milling strategy is used. This path cuts the internal right-hand 5/8 thread using a thread mill cutting tool. The path uses a linear approach motion and radial engagement and retract motions. The actual machine part is also shown here. Let's have a look at the complete cut material simulation of this setup in Visual Mill. We want to extend a special thanks to Dr. Casey Kerrigan and her team at OESH Shoes for allowing us to share her extraordinary success story. To learn more about Dr. Kerrigan and browse the OESH inventory, we invite you to visit them online at oeshshoes.com. To read this and other exciting case studies, we invite you to visit the MecSoft.com case studies page at MecSoft.com/case studies. To learn more about the great team at CNC Masters and the Super 3-axis vertical mill, we invite you to visit them online at cncmasters.com. To learn more about each Visual Mill feature and to download a demo, we invite you to visit the Visual Mill product page at MecSoft.com/visualmill. This video was brought to you by MecSoft Corporation, your CAM partner.